I'm going to talk about t-tests in this video. I'm going to show you a very quick way to do a t-test in Excel. A little bit of background about t-tests. T-tests are a type of parametric statistic, so it's a statistic that's based on a distribution, and it's a test that's used for comparing the means of two samples to see if those two means are different from one another. It's a very robust test, and it's very effective when you're looking at two populations and you want to know if they're different. So here is a very small example data set. This is a small enough data set that you could actually use a t-test formula and do a t-test by hand on it. But we're going to do one in Excel, so it'll be even faster. So this is a data set of body mass, and I should type that in as mass rather than weight. Body mass in grams of red-breasted sapsuckers in second growth forest and old growth forest. And we may hypothesize that there may be a difference in body mass in those two habitat types. Body mass is an indicator of health and fitness for many birds, and so we might make some predictions about that, how the different habitat and resources found in second growth and old growth forest might influence the body mass of red-breasted sapsuckers. So we collect a data set. This is a very small data set, and so I'd say if you really wanted to know this, to answer this question, you want to collect some more samples, but we can still run a statistical test on this data set to see if what we're observing so far is reflecting some real difference. So the first thing I always recommend that people do when they're starting to run a statistical test that gives you a probability is to first do some visualizations on your data. Look at your data, get some descriptive statistics, make a chart or two so that you understand the data before you run a test. Because once you get a test result, you could have gotten it erroneously, but it's hard to know if that's the case if you don't have any kind of descriptive statistics to reference. Now, in a lot of statistical packages, you automatically get the relevant descriptive statistics that are important to making the calculation for that hypothesis testing statistic. But in Excel, you're often just getting a probability value. So it's important, particularly important if you're using Excel in that way, to get these descriptive statistics and understand your data. Plus, when it comes around to presenting it, you need to know what those statistics are actually telling us. So here we are. We have two samples from these two different forests. The first thing I want to know is, what is my sample size? Now, with a very small data set, it's very easy to count these up. 1, 2, 3, 4, 5, 6, 7. So I have 7 in second growth and 1, 2, 3, 4, 5, 6 in old growth. If I have a very large data set, I can use a count function, and it's free of errors as long as you're selecting the correct range of data to be counting. And what a count function does is it counts the numbers of cells. There's different kinds of count functions, but it counts the numbers of cells basically that aren't empty in your data set. And so you can do a count function by either equaling typing in the code for that, which is equals count, or you can go up, select the cell where you want the output to be, and select this f sub x function icon. And you can search for it. You can type in count. It so happens that it pops right up because I just used it as the first function in this box. So I'm selecting count. And then I select a range of data where I want to count the non-empty cells. And then I hit enter and OK. And I have a count of 7. That's my sample size. I can drag that equation over to this other column, and it drags that over and references the same range of cells in column C that it did in column B. And so I get a sample size of 6. These are both correct. And now I know my sample size. The next type of descriptive statistic that most people want to know about is the mean or the average. This is an estimate of the center of your data, roughly. And if your data are roughly normally distributed, a mean is a great estimate of the center. And so you can easily compute a mean here by hand or in Excel by adding up all of these masses and dividing by the sample size. You can also use an average function in Excel to do that. And so again, I'm going to select in the cell and select the function key and then select average. If you don't see the function you want, you can type it in up here and Excel will search. There's hundreds of functions that Excel can use, or many, many dozens at least, to calculate for you. So I'm going to select average and select OK. And again, I have to make sure that Excel is selecting the correct range of cells. In this case, it's actually selecting the range of B3 through B10. That's including my sample size descriptive statistic, and I don't want to include that. So really, I want to just be selecting B3 through B9. And there is my average value for sapsucker mass in second growth forest. Again, I can drag this equation over to the column with old growth forest observations, and I get the mean value of 44.38. Okay, and so I see that these are different, but we don't really know if these are different. For one thing, I've only measured a total of 13 birds, 7 birds in old growth and 6 birds, or 7 birds in second growth and 6 birds in old growth. I need a larger sample to be sure. But even with a larger sample, I would need some other metric. I would start to need to see what the spread of my data are like. You can estimate a center, but you might have a huge range of numbers around that center, and minute differences in the center are not really reflective of anything in reality, okay? And so, because we're dealing with samples and not whole populations. So I might want to start, though, visualizing these data. And so I could insert a chart that reflects these means. And I'm just highlighting these two mean values in the two columns. I'm selecting bar chart, and here I have 2 bars. And so I can give this chart a title. Generally, when we're doing scientific papers, we omit the chart titles, and instead we type in a figure caption. We do that in the Word document where we're doing a write-up, but we could do this here, figure 1. Okay, so there's a figure caption, and it's reflecting what we have right now. But what we aren't seeing, all we see here is a 1 and a 2. And I think it's very important to immediately make sure you're correctly labeling your chart. So we're going to add a chart element. So I went up here to the upper right corner and selected chart elements. And I'm going to select first axis titles. And here for axis title here, I'm going to say habitat, forest type. And for this axis title, I'm going to body mass grams. And then for these numbers, I need to replace these numbers with actual values. So I want to also have this number 1 and this number 2 instead labeled as second growth and old growth. And it's easier to do this right at the beginning, but we can also insert that information here. So I'm actually selecting this entire row, and I'm going to copy it, and I'm going to insert it above these mean values. Okay, and then what I'm going to do is I'm going to go into the chart itself and go into this categories. And so I'm going to actually select these labels as the categories that will label the 2 bars. And now I have a chart that tells me what it's representing, okay? And so I have forest type, second growth and old growth, and I have body mass. And so what I can see here by comparing these 2 bars is that body mass appears to be lower in the second growth compared to the old growth. But I really don't have any idea of what the range around that number is, or what the variance around that number, the estimate of variation around that number is. So that's the next thing I want to do, is I want to get an estimate of variation. A very common one is standard deviation. And standard deviation is an estimate of variation around the mean of a data set. You actually calculate it by taking individual samples, subtracting them from the mean value, squaring that value, and then doing that little extra calculation, you get this estimate called standard deviation. And it's a really nice estimate of spread in a data set. And so here we go. We're going to do that using a formula in Excel. And I don't see standard deviation here, just up in the menu, so I can type it in. See if it comes in. Okay, so I typed in standard, and lots of stdev functions appear. So the first one that appears is standard deviation.s, estimate standard deviation based on a sample. This standard deviation is an earlier version of that. So we can do that. We can select standard deviation S, select OK. And again, you're going to select the range of cells that represent your samples. And I'm doing that right here. And I get a standard deviation now that I can drag across. So I have two values for standard deviation, one for second growth, one for old growth. Standard deviation can actually be plotted on a bar chart and compared. And so if I wanted to do that, I could go back into my bar chart and I could add error bars. So if I go back into this chart elements, I can select error bars, and actually Excel will start to generate those automatically, but they're not always the right error bars. So I will always select custom here. And you do that by hitting this error, and then you select more options, and then you go to custom, specify value. And you then go to the two values you want to represent, this one and this one. It's both your plus and your minus. And select OK. Okay, so now I have error bars that represent one standard deviation. So I need to add that to my figure caption. Right. And so these error bars, you can start to look. And what you're looking for when you're comparing error bars is you're looking to see how much they overlap. Some overlap is okay. You may actually really have differences in your population. There's some overlap in how much variation there is. But there are different kinds of error bars that might be more representative depending on what you're measuring. So standard deviation is a very common kind of error bar. So is standard error. And what standard error is a calculation of basically, it's very similar to standard deviation, but it's a sample of estimates of means that would be this range of variation. And so you get standard error by taking your standard deviation and dividing it by the square root of the sample size. So we can actually enter that formula here. We're going to type an equal sign, and then we just select the standard deviation value, hit the backslash for divide, and you type in SQRT, and then you type in 7 in this case, because that's our sample size, or I could select that cell with 7 in it. And that's my standard error. And that's a calculation I can actually drag across here, except for I have to make sure I've adjusted for sample size, because my sample size in the other sample is 6. So those are my standard errors. And sometimes you will see that error bars represent standard error. So when you start to see bar charts comparing two populations, one, always look for error bars. If there aren't error bars, you need to wonder why there aren't. Two, once you see error bars, the figure caption needs to tell you what they represent, because they could be representing standard deviation, standard error, or what we call 95% confidence interval. And they're all pretty commonly represented in the literature. So you need to know what these bars are representing. And so I'm going to show you what these error bars would look like if we had standard error being the thing that's represented. And so I'm just going back and I'm going to do a custom error bar again. And instead of selecting this range that's standard deviation, I'm selecting a range that's standard error. Okay. You can see that the bar chart has adjusted and the error bars definitely don't overlap. Okay. But I also have to change my text here to say standard error. And so people who know how these are calculated realize that standard error bars tend to be narrower than your standard deviation bars. Another calculation you can do is 95% confidence interval. I like 95% confidence intervals because when you put those error bars, you're looking at basically a range that represents what we would expect to find. Those bars are representing sort of an upper and lower bound of how a 95% level of confidence is around what the mean estimate is. And so if you look to see if they're overlapping, you're getting very close to something that looks like what a t-test is doing. Okay, it's not exactly the same, but it gives us the best sort of comparison to something like a parametric statistic with a probability value of 0.05. And so I'm going to do a 95% confidence interval, and this varies in different types of tests, but if you have data that approach normal in distribution, the 95% confidence interval is usually 1.96 times the standard error. And so we can just type that in. Times standard error, okay? And so we have this value here that is now our 95% confidence interval. And I just drug that formula across. And again, I can go back to my chart and I'm gonna change my error bars one more time to be 95% confidence interval. And I do that by selecting custom error bars, and for the upper and lower bounds of my bars, I'm selecting these values for 95% confidence interval. Okay, so now I have this bar chart and I need to change again the text. Error bars represent 95% confidence interval. Okay. Now I'm looking at this, and if I were to take a ruler, and actually these bars in the background of the chart these lines help us to make this comparison, we can see that these bars are not overlapping. In fact, there appears to be a little space between them. And so I think that probably, even with the small sample size, and this may just be a fluke because it's such a small sample size, but at least given the sample size I have, there appears to be a difference in second growth and old growth. I want to associate some kind of probability value to that. And that is what we call hypothesis testing in statistics. And the way a hypothesis test is structured is you're forming a hypothesis. So the hypothesis I had going in is that I think that there might be differences in those two habitats that influence body mass and sapsuckers. So I think there is a difference. That is called my alternative hypothesis. And that is sapsucker body mass differs in second growth. Okay, a null hypothesis is always paired with an alternative hypothesis. And so the null hypothesis is always a statement of no effect. And so this would be that there is no difference. There's no difference in body mass of sapsuckers between old and second growth. And when we run a t-test or any other statistical test, we're testing to see the probability. We're testing to know if the probability that the null hypothesis is true. And probability values range between 0 and 1. and they're usually some value that's 0 point something, okay? 0 point something. And so if you have a probability value of 0.9, the probability that your null hypothesis is true is very high. If you end up with a probability value of 1, it's almost like saying there's a 100% chance that your null hypothesis is true, that there's no difference, okay? And if that were the case, I'd be looking at a bar chart where the bars are exactly, if my p-value was 1, my bars are exactly at the same level as are the error bars, okay? In fact, the error bars would be almost non-existent probably. And so with the high p-value, like 0.9, again, I would be expecting to see actual bars that are the same and error bars that aren't offset hardly at all. So that is high probability the null is true. Okay, and what we say is we cannot reject null. It's so high. Now, if I have a p-value that's closer to 0, say it's 0.0001, then you would reject the null hypothesis. And what that's actually saying is there's a very small probability that your null hypothesis is true. It's almost 0 chance that the null hypothesis is true given the data that we're looking at. And so when you are running a hypothesis test, you're looking for a small p-value. And in many areas of biology, the cutoff, the significance, excuse me, my spelling, level, or sometimes they call it the alpha, is p is equal to or less than 0.05. That's what we're looking for, a value that's 0.05 p-value or a smaller value will tell us that we can reject the null hypothesis and say that there really is a difference that we're observing. So now this is for the very quick thing that we're going to do here, and that's the t-test. And so I'm going to say t-test p-value, because this is what Excel gives us. It gives us a p-value. And so if we go into Excel and we select a function, we can select the function, and I can type in t-test. And there is a function here for t-test, and I'm going to read it. This function is available for the compatibility with Excel 2007 and earlier, returns the probability associated with the student's t-test. So it's a compatibility function. Let's just type in t. There's a t-value. There's a t-test here, and that's probably the one we want to select. I'm going to try to select something that's more current. And so this returns the probability associated with the student's t-test, which is what we're doing. So it's t.test. I select OK. And so what they're going to ask us for is 2 ranges of data, range 1 and range 2, or array 1 and array 2. That's the first thing you enter for this test. And so our first array is going to be second growth. And we highlight those mass numbers for second growth. Array 2 is going to be old growth, and we're going to select that range of numbers for old growth. Tails. And we go into tails. And so when we're envisioning a t-test, we're envisioning something that's very similar to a bell curve, a t distribution that's similar to a bell curve. And it's asking us if we are making a specific prediction that sapsuckers will be heavier in one habitat and lighter in the other. And generally in ecological statistics, we're not making that prediction that there's a directionality to it. We're predicting that there's a difference. And so that's what we call two-tail. So the difference could be on this side of the tail or this side of the tail. We're not saying which one is which. And so we use a two-tailed test. Then finally, we have to select the type of t-test. And so there's a variety of different kinds of t-test. There's a paired t-test, which is for making usually before and after comparison. So you're looking at the same sample, but something's changed with that sample and you're comparing to see if the change has an effect. That's not what we're looking at here. There's a two sample, and that's definitely what we're looking at here is two samples. We've collected two independent samples in two different habitats. And the first two sample is assuming equal variance. And that means the variation around the mean is equal. And it looks like it really probably was in our case, but we didn't test that. There's also one called a 2-sample t-test with unequal variance. And that is the more conservative test for us to be taking. We don't know if our variances are the same. It becomes harder to reject the null with this type of t-test. But if we do reject the null, it's a little bit more of a robust answer. So I'm going to select 3. Okay. And now I have a t-test value. I have a p-value right here. It's 0.0042 or 43. So my p-value is 0.004. It is much smaller than 0.05. So I can say there is, so this is equal to reject the null. I'm not going to say equals here because it's going to tell me to do a formula. Reject the null. And so there is strong support that the alternative hypothesis is true, okay? That there is a difference in body mass between the 2 habitats. And that is very congruent with what I'm seeing here with my bar charts. And I can say in particular that old growth body masses are higher than second growth. So there's a t-test.